All right, so when a glucose ring closes, when you have a Fisher projection and it closes and it becomes a Haworth projection, it depends on the direction of the carbonyl of the aldehyde. If the carbonyl was pointing down, it closes with an OH pointing down. If the carbonyl was pointing up, it closes with this pointing up. It's a 50-50 mix. So anytime a glucose closes, it could, at carbon number 1, the OH pointing down, or it could be pointing up. The rest don't change. These are pretty rigid. So carbon 2 will always be down, carbon 3 will always be up, carbon 4 will always be down. That's just the way it will always be with a D-glucose in the ring. But this can change. If the OH is pointing down at carbon 1, the one that used to be the carbonyl group, this is called alpha D glucose, because we started off with the D glucose, and the thing that we changed now, or that we added in, is this term alpha. Alpha is telling you what direction the OH is pointing at carbon number 1. This makes a really big difference when we start creating bonds to create disaccharides and polysaccharides. So we have to indicate always, is this an alpha or is it a beta? If I wanted to switch this and turn it into a beta, all I would do is this. Now it's a beta D glucose, okay? Only carbon 1 will change. Alpha, beta, alpha, beta, alpha, beta. Depends on how that hemiacetal is forming. And the hemiacetal is the thing that is created between carbon 1 and carbon 5. That's that reaction of the aldehyde with the alcohol of carbon 5. So this over here, here's your hemiacetal, okay? Now, to make your life easier, you can do line drawings of glucose. So basically, I'm getting rid of all the carbons, all the OHs, sorry, not OHs, don't get rid of the OHs, all the H's, and just focusing. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Looking at this, you can tell that it's glucose because the OH is pointing down at 2, up at 3, down at 4, which is what we did when we turned that Fisher into the Haworth. You can also tell that carbon 1, the OH is pointing down, so is it an alpha or a beta? Remember, down at carbon 1 is alpha, up at carbon 1 is beta. Okay? Now what I want to do is turn a galactose Fisher into a Haworth. Do you guys remember how I told you that glucose and galactose are epimers and they differ at which carbon? They differ at carbon 4. So all you have to do, if you want to turn this glucose into a galactose, you just count. This is carbon 1, 2, 3, 4. Remember how galactose was pointing to the left at carbon 4, but to the right on the OH was pointing to the right on glucose at carbon 4? So all you do to turn this into a galactose is just put this up. And there you go. This is alpha D galactose. Now, if you want to draw beta D galactose, it's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Carbon 6 is outside of the ring. Carbon 1, the OH pointing up, that immediately tells everybody that's a beta. This is carbon 2, carbon 3, carbon 4. Look, carbon 3 and 4 both pointing up in galactose. This is beta D galactose. Students will always tell me, well, Dr. Robbie, how are we supposed to know which to draw? Well, if you're going to draw this one, name it correctly. It's beta D galactose. If you're going to draw this one, name it correctly. It's alpha D galactose. Okay? It's as simple as that. And it's just remember, it's like a 50-50 mix of both of them. So if you're going to draw an open chain Fisher, just draw it open chain Fisher, and you don't call it alpha or beta. But if you're going to create a ring, then you have to indicate if it's alpha or beta. All right, fructose is a little trickier. Fructose is the ketone group is going to connect with the furthest chiral carbon. So I'm going to draw an open chain fructose right here. Carbon 3 points this way, carbon 4, carbon 5, and carbon 6. So this is fructose. This happens to be D-fructose. Why is it D? Because, like we said, furthest chiral carbon pointing to the right. All right, so with fructose, it's the carbonyl group is going to create a hemiketal with the furthest chiral carbon OH, alcohol. And notice now carbon 1 and 6 are outside the ring. They're not part of the ring. So turning this into a Haworth projection, I'm not going to show you the details, but I'll show you what it's going to look like. It's going to look like a pentagon. It won't look like a hexagon anymore. It's going to look like a pentagon. The other thing that looks like a pentagon are the pentoses. Ribose and deoxyribose are both aldopentoses, so they're going to form hemiacetals, but their ring is going to look like a pentagon. The aldohexoses look like a hexagon, but fructose, because these two guys are not part of the ring, it looks like a pentagon. So you'll see what I'm talking about. So I'm going to do a beta D fructose. That's what I'm going to do. This is carbon. Actually, let me go ahead and draw the pentagon here. All right, so this is carbon 2. Remember how I told you, carbon 1 is not part of the ring. So I'm just going to put carbon 1 here, CH2OH. And because I want to do a beta, the OH at carbon 2 is pointing up. Remember how I told you with glucose and galactose, carbon 1 OH will tell you if it's alpha or beta? Well, because those are aldehydes or aldoses. Fructose is a ketose, and so we focus on carbon 2 to tell us if it's alpha or beta. This is carbon 1, this is carbon 2. So carbon 2, the OH is pointing up, so therefore it's a beta. Carbon 3, here's carbon 3, it's pointing to the left, so it's going to go up here. Carbon 4 to the right, so it's going to go down. Carbon 5 is this guy, and this O used to be this OH here, so it's already part of the ring. Carbon 6 is CH2OH. So this would be a ring for beta D fructose. If you want alpha D fructose, what would you do? You just flip this over. The OH comes down, carbon 1 comes back up again here. All right? All of this is drawn in your textbook, and you could look all these things up. I just wanted to show you how you turn all the Fishers into Haworths. Now we're ready to move on to disaccharides. And in order to create a disaccharide, you need to have two monosaccharides bonded together. And the bond is called a glycosidic bond. Now, whenever people talk about simple sugars, they mean the monosaccharides and the disaccharides. And then you know how they talk about complex carbohydrates? Well, that's anything more than disaccharides, okay? So let's try to draw the simplest of the disaccharides. We're going to learn a bunch of structures, but the disaccharide, the simplest one is just maltose. So what I want you to do is to draw an alpha D glucose and another alpha D glucose. So we're going to put them right next to each other. And I'm just going to do line drawing so I don't have too much clutter here. Okay. Here is alpha D glucose. Why is it alpha? Carbon number 1, OH is pointing down. And then here's another alpha D glucose. Okay, carbon 6 is outside the ring. All right, so when you create a bond between two monosaccharides to create a disaccharide, you remove a molecule of water, okay? And you end up creating something called a glycosidic bond, which is basically a carbon, oxygen, carbon bond. Let's take a look at carbon number 1 and carbon number 4, because the bond is going to be between carbon 1 of this monosaccharide and carbon 4 of this monosaccharide. Maltose is made up of 2 glucoses, okay? 2 glucoses. So this is an alpha D glucose, and so is this one. And what we're going to do is we're going to remove a molecule of water, HOH. So it doesn't matter which OH you take and which H you take, but can you see the potential for removing a molecule of water? So let's say I'm going to take this OH and this H. Now this is what's super important when you're drawing structures in biochemistry. Keep the bonds facing the proper direction. So if this is pointing down, keep it pointing down. If this is pointing down, keep it pointing down. But you can scoot it over a little bit so it looks a little neater. So this is pointing down, keep it down. This is pointing down, keep it down. Just put the oxygen in the middle. And you've created your first disaccharide. This is maltose. The bond that connects them is called an alpha 1,4 glycosidic bond. Why is it alpha 1,4? Because this is alpha, it's going down. Why is it 1,4? Because this is carbon 1 and this is carbon 4. Now we take a look at this carbon over here. This is that hemiacetal, right? This is the hemiacetal that we created. And this hemiacetal can open up and become the original aldehyde and close again. Open and close. If it closes with the OH pointing down, this is an alpha maltose. And right here, I know we started off with an alpha D glucose, but remember these things can open, close, open, close. So right now, the way we drew it, we're just going to write alpha maltose. I'm just going to drop the D for now. And that's our first disaccharide. Okay, we'll do a few more in the next video.